All right. Good evening, everyone. I would like to extend a warm welcome to Abhinav Deshpande, along with all the attendees for our event on behalf of the Research Society MIT. He will be inaugurating our event, Cognizance, with his talk on quantum computing, the future. Cognizance is an initiative which hopes to bring together all people interested in research in various fields. Our organization is confident that this talk will provide value to everyone attending. Before the presentation begins, I would like to define the structure of the talk today. Our speaker will be giving a presentation on the topic, followed by a question and answer session. Throughout the talk, the chats will be open to discussion for all the attendees. You can interact amongst yourselves if you would like to, and can also put up your questions here as well. And we'll be asking them to Abhinav at the end of the presentation. Even though our team will be moderating the chats, we would like to request everyone to keep the contents of the chat related to the topic. Having said that, I would like our moderator, Dhyan Gandhi, to introduce our speaker for the day.
Yeah, thank you, Suprati. Uh, I'd like to introduce our speaker for this talk, Abhinav Deshpande. Abhinav is a doctoral candidate in physics at the University of Maryland. He is a research assistant at the Joint Center for Quantum Information and Computer Science and the Joint Quantum Institute at Maryland. He has completed an integrated master's in physics at IIT Kanpur. He was also a KVPI fellow. With 14 publications in the field of quantum computing, he has received over 150 citations in his work. We are very excited to host him, and I am sure we'll all gain some very valuable insights in this topic. With these few words, I'd like to humbly request Abhinav to give the talk.
Hi. Thanks a lot, Dhyan, for that very kind introduction. And thank you all for coming. Um, yeah, so today I'd just like to talk about quantum computing, which is a field of research that I work in. And I'd like you to gain from this talk a little bit of a flavor of where we are headed. So yeah, I belong to these two institutes, which are part of the University of Maryland. Okay. Yeah, so let's begin. So a couple of you, or like, yeah, maybe a lot of you have already seen this news event from October 2019, where Google announced something known as quantum supremacy. And their CEO posed with this, weird looking beast. You may ask what that thing is. And, they say it's a quantum computer. So other news outlets such as Wired also regularly cover quantum computing. So this is like a snapshot of their recent headlines, for example. Well, and it's no doubt that quantum computing is bigger than Donald Trump, for instance. Well, yeah, quantum computing has also been in the news for various other reasons. Some of them are arguably a bit more hyped, such as whether it can solve global warming or whether you can buy your own quantum computer for like $10 million. But among the less hypey things, so there's recent news that a new quantum computing startup, IonQ, is planning an IPO. So it went public. So given all this excessive reporting over quantum computing, it is fair to ask whether quantum computing can live up to its hype or not. And again, so there are differing answers here. So for example, one expert wants that the field is overpromising, and the other says, oh, maybe it's not, and we're just on the verge of building something useful. So, okay, let's step back a bit and ask what's all the fuss about. And that's what I'll hope to cover in this talk. So we'll answer these questions of what is quantum computing, how it works, and why people are excited in this field, who is building them, and when will I get one? Okay, so let's begin here. Oh, and I should say, yeah, like if there are any pertinent questions, feel free to unmute and ask me. Yeah, I would like this to be interactive. Okay. Um, so quantum computing is a field of science which is at the intersection of quantum physics and computer science. So that's the very simple definition. So in the coming slides, I'll just explain a bit more about what these two fields are and what questions they seek to answer and so on. So computer science is again like one of the great intellectual achievements of humans in the 20th century. And the central objects we deal with in computer science are computational problems like sorting numbers or arithmetic operations like adding numbers and so on. You may think of more complicated tasks which are at their core just chaining together a lot of elementary operations. So these more complicated tasks could be simulating robots, playing chess or Minecraft and what have you. So a computational problem is defined by what the input to the problem is and what the desired output or the outputs to the problem is. And we'll see an example soon. And an algorithm is just a bunch of elementary steps that solve a particular problem. One example is Euclid's algorithm from way back in the BCs. I don't know when exactly. That solves the problem of finding the greatest common divisor of two integers. You may have seen this in school. So the problem there is you're given two integers, and yeah, you just want to find the greatest common divisor. And Euclid's algorithm is very simple. It's a series of repeated divisions, and yeah, at the end you just have the answer. Okay. So now, yeah, let's come to this idea of Turing machines. So it turns out that all classical computation can be modeled by a Turing machine. So this covers computation, right from like just a basic calculator to the most advanced superconductor computer that exists today. So Turing machines have the following. So there's an input tape on which there's a series of symbols, zeros, consisting of zeros and ones. And there's enough to specify any input, because as you may all know, like classical computers just represent data using zeros and ones. And so there's another work tape where there's some blank symbols and some other filled symbols. And there's something known as a head, which you may think of as like a CPU. What it does is it has a very small set of rules and some internal states. And a typical rule is something like if what you read is 0 and if the work tape is blank and your head state is something X, then go to some other state and change the symbol. Okay, so the specification of a Turing machine is just a collection of simple rules such as this. And it turns out that just a very simple model like this can capture all of computation, which is pretty neat. Okay, yeah, so we are often interested in what the optimal algorithm is for a particular problem. But there's, yeah, when I say optimal, you may ask, like, how are you comparing two different algorithms? So one thing you could do is, you just implement both algorithms on your laptop and see how much time elapses at the end. So this is called wall clock time. So you just look at the clock and say, oh, it's 4 minutes or 5 minutes. But this has a few disadvantages. One thing is that this depends on how fast your computer is. So yeah, if you report to me that solving problem X takes 5 minutes on your laptop, I have no idea how fast it would be to solve that problem on my laptop. Okay. Um, also, this also depends on how large the task is that you want to solve. It could be that, yeah, if I'm sorting a larger list than you, then the time I would take would be longer. So to solve this, what we do is we look at the number of elementary computational steps that you need in order to solve a problem, and you can define a standard Turing machine that simulates every other thing, and you can ask how this number of steps scales with the size of the input. And computer scientists usually denote this as n. Yeah, so coming back to the example of sorting lists of numbers, there's an algorithm called merge sort, which takes time order n log n, whereas bubble sort, which is a different algorithm, takes time order n squared. Okay. And many problems are something like this. So they have algorithms where the runtime scales at most as a polynomial in n. So that means the time could scale as n to the k for some constant k. Sometimes it can be as bad as n cube or n to the fourth, but that doesn't matter. We still call them, yeah, we still regard them as efficient in some sense, which brings me to my next slide. Yeah, so we call a problem efficiently solvable if there is such a polynomial time algorithm that solves this problem. So yeah, examples are sorting and finding the GCD of two numbers, etc. And so we categorize this into something known as a complexity class, and the complexity class is called P, which is short for polynomial time. And that's the set of problems efficiently solvable on a regular computer. Yeah, so sometimes I'll say classical, and I use classical to distinguish it from quantum. So classical just means non-quantum. Okay. Yeah, so there are many problems that we do know how to solve in polynomial time, but there are also many problems where we don't know how to solve in polynomial time. For example, there's this problem called Hamilton path or Hamiltonian path, which asks whether there is a path in the graph that visits all vertices exactly once. So it can't go back to the same vertex again, but it has to visit every vertex in the graph. So for this particular graph, there exists one. So you start here, and you go to E, then A, C, and B, and F, and so on. So that's a Hamilton path. So the answer to this question is yes. But in general, we don't know of ways of solving this problem that are much better than trying out all the paths. So this is Hamilton path is an example of a problem that is probably not efficiently solvable. So it's probably not in this class P. And a major goal of computer science is to either come up with good algorithms for the large set of problems. And when I say good, I just mean efficient in the sense that I just defined here. Or if it turns out that that you don't find a good algorithm for some problem, then you want to understand why, and and also try to figure out ways to get around it. Okay. Any questions so far? Okay. If not, let me move on to the next part, which is talking about quantum physics. Quantum physics is one of the other great discoveries of the 20th century. And the fundamental concept involved in quantum physics is that of superposition. And I think you may all have heard about Schrodinger's cat, where you imagine that there's a cat in a box, and there's a radioactive atom or a set of atoms nearby, and with probability 1/2, it's going to decay and set of things that will cause the cat to die. And with probability 1/2, it will not decay and the cat will remain alive. So quantum mechanically, the way we describe the state of the cat is just via a two-dimensional Hilbert space. So that's a lot to unpack. What you can just think of alive and dead as just two vectors. And you can sometimes have, okay, let's make the description a bit less gory. Let's call it awake and asleep. So you can have states that are neither awake nor asleep, or if you like, both awake and asleep. So, and these states are described by these other arrows in this space. And it turns out that actually many weird properties of quantum mechanics are simply implications of this fact that you can put an object into states like this. So it's neither this nor this. Yeah, I think maybe I can give another illustration of this concept of superposition and also interference. And things will get a bit more mathematical. So you're forewarned here. So what we have here is an interferometer. What that means is you might think of it as just a thing that splits light. So there's light that comes in from here, and one just represents, let's say, the intensity. So you have 1 watt of light coming in over here. And what this beam splitter does is it splits the light. So some of it is reflected and some of it is transmitted through the beam splitter. So you may also imagine sending light from the other direction here, and it still does the same. So some of it is transmitted and some of it is reflected here. But the difference between these two events, so notice that there's this black line here. And what that indicates is the light that's reflected off of this surface carries an extra phase of a negative sign. Okay, so that causes some interesting things to happen. So now when you have light entering from, say, both these, you may imagine them as ports, what happens is that all of the light goes through this direction, and there's no light passing out from this direction. And that's happening precisely because of this negative sign that I said here. So it turns out that the wave here and the wave here are equal in strength but opposite, and they cancel each other out, whereas they reinforce each other on this port. We'll see that more mathematically now. So yeah, I'm just denoting these directions in this funny notation. That's just some notation used for vectors. So don't worry too much if you don't get it. So the action of the interferometer is just described by this matrix here. So if I have some light coming in from top and from the left, and I apply this matrix on it, I can see how much amplitude is going into these two directions. Yeah, and this negative sign is precisely because of this phase here. So Born's rule in quantum mechanics is a way of getting at actual probabilities from operations we do to the quantum state. So what it tells us in a nutshell is when you have a state, you just take the modulus squared of an amplitude and you get the probability. So the probability actually translates to intensity here. So yeah, it'll be clearer when I show this example. So when you have this experiment, when light is just coming in from top, so it's only the top thing that's initialized to 1, and so there's no light coming in from the left, so I put a 0 in there. And when I multiply out these two matrices, what I get is 1 over square root 2 and 1 over square root 2 in both the right and the down directions. And what Bond's rule is saying is you take the square of these quantities. So I get 1/2 and 1/2, right? 1/2 and 1/2 going into the right and the bottom directions. Yeah, so similarly, we can also explain this experiment. So now when I put in light only in the left port, and there's no light on the top port, so that's why this corresponds to a 0 and a 1 here. And I multiply these matrices out. I get a 1 over root 2 and a minus 1 over root 2. And again, when I square them, I get 1/2 and 1/2. So I again get that the light splits equally between the two ports. So now this is enough to understand what's going on here. So when we put light in both these ports, we're initializing the vector to 1 and 1 now. And just because of matrix multiplication, everything cancels in this bottom row, and you get a root 2 upstairs. So the root 2 then, because of Bond's rule, just becomes, just translates to an intensity of 2 in this right direction, and no, 0 intensity in this bottom direction. Yeah. If there are questions here, I can pause and wait, because I think this was a lot to take in.
No, I don't think the audience has any questions as of
Perfect.
now.
Okay. Yeah. So let me move on. Quantum computing is actually just a generalization of this idea of interference. So what we saw is that we could engineer things in such a way so as to get a cancellation in how much light is going down here. And what we want to do is, in quantum computing, is more of the same, really. Yeah, so one fundamental ingredient in quantum computing is that of a qubit. So instead of a bit in classical computing, you have a quantum bit or a qubit. And now you say that you can put it in superposition of states, like A0 plus B1. Okay, this is how we denote this superposition of states that I mentioned earlier. So when we have two qubits, it can have any state like this. So yeah, this is the state of the first qubit, and the second one. And you can have all 4 possibilities: 0, 0, 0, 1, 1, 0, and 1, 1. So when I go on adding qubits, n qubits can actually be in a superposition of 2 to the n states. And this is exponentially large. So right, and just to give you an example, exponential growth is really fast. So when we have 17 qubits, the number of states that we'll have will be almost nearing 150,000. Okay, and actually, this can go both ways. It can both help us and harm us. So we'll see a bit more about what the difficulties this presents. So one difficulty is that if you have a quantum system of 300 qubits, you can't even write down the state of that 300 qubit quantum system in the entire universe, because 2 to the 300 is more than the number of atoms in the observable universe. So there's no way we can hope to simulate a system like that. But on the other hand, we can turn it around and use it to our benefit. We can harness this exponentially large Hilbert space. And that's what we're doing in quantum computing. We have to orchestrate careful cancellations in the state space, um, and hope that this somehow gives you a large probability of getting the correct answer.
Abhinav, sorry to interrupt. We
Yeah.
had a
No.
question
Okay.
that was asked. How did we arrive at the equation, the one, the matrix equation in the previous?
Uh, you mean just the description of the matrix, 1, 1, 1, minus 1? I
Yeah.
think that comes out from, yeah, actually, this is not too much quantum going on, although you can still describe this quantum mechanically. This is more of just wave behavior. Waves can interfere with each other and cancel each other out. That's essentially what's going on here. Um, yeah, and it turns out that reflection from this black surface gives you this phase of -1, which is essentially the main thing that we used. Yeah, I hope that helps. But if not, feel free to ask me again at the end.
Okay. Thanks.
Yeah. So quantum computing, in a nutshell, is understanding the implications of these new rules for manipulating information. Um, yeah, it's this realization that our world is actually quantum and not classical, and that just turns out to have um, a lot of implications that weren't really accounted for at the beginning. Okay. Yeah, so you may ask, how does it work now? So this is actually a fun picture of a quantum computing lab at the University of Maryland. And yeah, as you can see, there's a lot going on here. Mm, yeah. So I'll just talk about like the gate model of quantum computing. Um, and this is a reasonable model of what we believe physicists can do in the lab. And recall that we care about how your effort scales with the system size. So yeah, there are reasons to believe that the effort that we are putting in only scales polynomially, in the, say, in the size of the quantum computer that we can build. Yeah, so let's cover the basic ingredients of this model. As I mentioned before, we have a qubit. So anything that has a two-dimensional space and you can put in superposition can be a qubit. So it could be, Schrodinger's cat even, if you're a sufficiently advanced technological being. And yeah, so we represent qubits in this two-dimensional vector space. It's a complex vector space, so you can have imaginary numbers to describe your states as well. And yeah, this is some, again, funny notation. So we are representing 0 in terms of a basis vector like this, and a 1 like this. So these two numbers just say how much 0 there is and how much 1 there is in the state that you're representing. And this is entirely the analog of the kind of vector I was writing here. Okay. Yeah. Yeah. So we have qubits, and what we want to do is we want to manipulate them. So there are single qubit gates that help you rotate anywhere within this two-dimensional space. And some single qubit gates are this X and the Z. So when you apply X on this 0 state, what it does is, yeah, if you multiply them out, you'll just see that you'll get this vector 0 and 1. So the X is just simply converting a 0 to a 1 and a 1 to a 0. And the Z gate is applying what's known as a phase. And it applies a phase to this one state. And all of these, so yeah, All of these are actually rotations in this space. And you can also apply fractions of rotation. So in this example, the vector rotated by an angle of 90 degrees. You can also rotate by less than 90. That's totally fine. And yeah, quantum mechanically, they're actually generated by this operation. Yeah, so other than single qubit gates, we have 2-qubit gates, which act on, say, 2 qubits at the same time. That's a no-brainer. So for example, we have a gate like this, C naught. What it does is if the first qubit is a 0, it does nothing to the second qubit. So that's explained by these two entries here. On the other hand, if the first qubit is a 1, then it flips the second qubit. So C naught stands for controlled knot. Yeah, and you need, so the C naught is a gate that sort of entangles 2 qubits because it kind of makes them interact.
We had a question in the chat. If you, uh, Soham is asking that how are qubits generated or simulated? For example, classical bits are represented as different voltage levels in circuits.
Very good question. So yeah, there are many hardware implementations of qubits in quantum computers. So as a community, we have not arrived at a unique way of representing qubits, and I'll cover them towards the end of my talk. Okay, thanks a lot for that question. So yeah, so a C naught is a 2-qubit gate. Yeah, and that's it. Yeah, so when we have circuits, these are just composed of single qubit gates, 2-qubit gates, and and so on. But first, I'll just talk about this concept of universality, which is that a simple gate set can actually generate any arbitrary rotation in this really large dimensional space, 2 to the n dimensional space. And yeah, you can, the time taken to generate an arbitrary rotation might take exponentially long in the worst case, but again, that's unavoidable. And one nice universal gate set is just given here. So we have this thing called a Hadamard gate, which actually rotates things between the x and the z bases. And there's something called a T gate, which is just a phase shift applied to like the one state, and the C naught that I showed you previously. So a quantum circuit looks like something like this. You start off in a product state, and a product state is just a string of zeros and ones, for example. And that's opposed to something that's a large superposition over many states. Okay, so you start off in a state like this, and in the first layer of your circuit, you apply some subset of these gates. H, you're applying, say, H to the first qubit, T to the second qubit, nothing on the third qubit, C naught on the fourth and fifth, and nothing on the last one, and so on. So you just keep applying more and more gates in each layer, and at the end, what you get is a state that's a really large superposition over 2 to the n states. So x here just represents a bit string, like like the one we saw here. So when we measure the output state, Bond's rule is telling us that you would observe a string of bits z, let's say, with probability alpha z square. Okay, so these are like the basic rules of quantum computing. Yeah, and so you may ask, okay, then what? Like, what does it mean? Yeah, so it turns out there are a few applications of what you can do with these rules, which is why we are all very excited in this whole field. Is there a question?
Yeah. Uh, Aditya is asking, have researchers arrived at any computational language to alter the states of qubits?
Uh, I think, yeah, let me see if I interpret the question correctly. Yeah, there are some programming languages that are specifically used for programming quantum computers. Um, yeah, and there's nice abstractions you can do, um, and this is also a whole field of research in itself. Um, yeah, but when I see quantum computing being taught in introductory courses, yeah, there's not a lot of these programming languages being used. Um, yeah, it's more, yeah, like we just write out what the circuit would be that does a particular thing.
Okay. I had a question that I wanted to ask actually.
Okay.
As a analog to classical gates, what exactly do these quantum gates actually represent
Um,
physically? I mean?
right. Yeah, so classical gates are and, or, and not, for example, right? So the control not has a very nice interpretation in terms of the analog of a classical gate, right? It's like you can think of a classical gate that does exactly what the control not is doing. Um, the Hadamard and the T gates are somewhat, uh, the interpretation for them is somewhat less obvious. Um, yeah, like I think these in this example, um, maybe the quantumness is more visible from these two gates rather than the C naught. But the C naught is also, an essential ingredient. Mm. Yeah, sorry, I don't think I can give more intuition than that.
One question that was asked previously is that what do these gates actually represent physically? Uh, yeah.
Yes. Um, so let's see. Yeah, so these single qubit gates, they're actually just representing how how you can rotate this vector around in this vector space. Um, so yeah, like for example, you can just go in the lab and apply like a magnetic field in the z direction, and that causes your let's say if you have a spin, a magnetic spin, which you can think of it like just as a compass, and you apply a magnetic field, then the spin just rotates around that axis. And these gates and actually fractions of these gates, they're essentially just capturing that rotation. Mm. So single qubit gates are somewhat well easy to understand in that sense, because they're just telling how much to rotate a qubit, a spin, and in what axis. Um, two qubit gates, on the other hand, are a bit more complicated. Like you can imagine this two spins, and how much this thing rotates depends on which way this spin is pointing. Um, so there's some interaction involved there. So that's one nice physical picture to keep in mind.
Yeah, that makes sense. Uh, can a C naught gate be used as a universal classical gate?
That's again a nice question. Actually, so the C naught by itself is not sufficient, but there's a 3-qubit version. So you have another control line, and what you do is you control on the first 2 qubits being in say 1, and then you flip the third qubit, and so that also has a nice classical analog, and it's just called the Toffoli gate in just regular computing. So if you're aware of the Toffoli gate, then you might also know that that's universal for classical computing.
Okay, we just have one last question
Yeah.
by Yashas.
Mhm.
What is the exact logic behind the lining up of those gates in the circuit?
The lining up of the gates in the circuit. Oh, so in this example, I just just randomly generated some from my own head. They're not really solving any interesting problem that's known to me, at least. Yeah, but there is a logic to say the gates that you apply in like Shor's algorithm or something like that, which will come to soon. Yeah.
Okay, thank you.
Okay. Yeah. So what are the applications of quantum computers? So one is for this problem known as factoring. Yeah. So if I give you a large integer such as this one and ask you to find its prime factors, then you might just think, oh yeah, that's a very hard task. But if I tell you that this this equality is true, that these are the two prime factors of this large number, then you might be inclined to actually multiply these two out and check that what I say really makes sense. So what I'm getting at is that this operation, multiplication, is easier than the reverse operation of decomposing this number back into two factors. And yeah, so that's just what I said. And actually, that's almost the entire basis of today's cryptography, including, for example, how this call is encrypted. Yeah, so this problem is known as factoring. And we believe that this problem is hard for regular computers, classical computers. And this belief actually underlies all of modern cryptography. And this is why you can actually trust sending your password or your credit card number or something like that to a remote server over the internet. Yeah, and when I said it seems to be hard to factor a number like this, the way to formalize that is that today's best known classical algorithms for if I want to factor like an n-bit integer, they take time roughly exponential in something n to the 1/3, but that's still exponential. It grows very fast with n. And interestingly, Peter Shor, a mathematician, discovered that quantum computers can actually solve this problem in polynomial time. So specifically, this takes time n squared, which we believe, which as you recall, was a criterion for what it means for something to be efficient. And this is Shor pictured here. And actually, yeah, these equations are actually describing, one subroutine of his algorithm. So another very promising application of quantum computation is that of quantum simulation. And this is Richard Feynman, who in 1982 actually came up with the idea of quantum computation precisely for this reason. And again, he was observing that to simulate like a quantum system, it seems to take a really long time. So he asked, why not build a computer out of that quantum system? And in some ways, the entire field is formalizing this insight that he had. So the high level idea, yeah, I just said it. Like, I think regular computers, when I say regular computers, this is a bit of a stretch. Find it hard to store a state even of 60 qubits because 2 to the 60 is a lot. And yeah, again, this is the observation that a quantum computer can simply mimic the existing physics and simulate quantum dynamics natively. And this is useful in a lot of areas like high energy physics, condensed matter physics, and quantum chemistry. So actually, quantum chemistry is one of the probably, I would say, near-term use case of quantum computation. because yeah, I don't know what factoring is good for unless you want to break someone else's encryption. Um, but in all likelihood, we'll have migrated to post quantum methods that would be also secure against quantum computers by then. So I think factoring is probably not like $1 billion industry, but quantum chemistry seems to be on the verge of being something like that. Well, not on the verge, but yeah, it has promise. And the reason is that a lot of problems in industry concern designing materials, or say drug design and so on, where you actually want to simulate molecules. And it turns out that you can just do it much faster on a quantum computer than on a regular one. Okay. I'll move on to a third class of quantum. Well, was there a question?
Yeah. So Aditya is asking, can general no-field sieve, which is currently the fastest algo to factorize primes, can it be implemented on quantum computers?
Yes, you can. So you can implement any algorithm that runs on a classical computer, on a quantum computer. You just ignore the, yeah, like it's quantum computing is strictly a superset. But that said, quantum computing hardware is much behind classical computing hardware. So for example, like just this laptop I'm speaking on has like 1 billion bits, roughly. But today's quantum computers are more like in the range of 50 to 70 qubits. So there's no real reason why you would implement classical algorithms on a quantum computer. Um, yeah, but if you wanted to, yeah, no one's going to stop you.
Okay.
Okay, yeah, I'll move on to some other kinds of speed ups. So there was this discovery by Love Grover in 1996 that you can get a square root speed up for some tasks. And actually, what he showed was that you can do unordered search quadratically faster than classically. And what that translates to, if you want to solve optimization, is that instead of taking something like 2 to the n time to solve a problem, you might take, say, square root of 2 to the n time. So that's 2 to the n over 2. And yeah, you might argue that's still exponential. Yeah, so like what really matters is how this is actually going to scale on interesting sized problems. So the jury is still out on whether 2 to the n over 2's kind of speed up is useful or not. Yeah, but we'll see. Yeah, they may still be useful. We're not sure. I'll cover quantum machine learning. Well, not all of it, but like some of the initial ideas. So it was realized somewhere around 2009 by Harrow, Hasidim, and Lloyd that you can solve exponentially large systems of linear equations quantum mechanically. And there's a small star here because you can't actually write out the entire solution. You can only sample from like a distribution that's correlated with the answer. But it can do sometimes. And Kernadis and Prakash came up with a quantum algorithm for recommendation systems. And this is roughly something like the Netflix problem, if you know about what I mean. So the problem is that you have a bunch of users who have certain preferences, and you are given a new user who, let's say, watches a few movies and likes some of them. And then you want to come up with a new recommendation for that new user, like a new movie for them to watch. And the whole reason why you can solve this problem, and why Netflix gives you good recommendations sometimes, is that all these things are sort of low rank, meaning that there's not that many users with who are very unique in some sense. Yeah, I don't know if that explained it. But anyway, so this quantum algorithm built off of the algorithm for solving these large systems of linear equations, and they came up with a way of giving you fast recommendations. And for a long time, people believed that this can be done exponentially faster than classical computers, until the algorithm itself was dequantized by Evan Tang in 2018. Was there a question?
Hello. Hi, Abhinav. Can you hear me?
Yes.
Yeah, hi. Okay, so my question was, I guess, more of a basic intuition-based question where, for example, I think you said that what gives quantum computing an edge over classical computing is because of the nature of the qubits to be in a superimposed state. Is that right? Like, that's what I've understood.
Yes, that's part of the reason. Yes.
Right. But like, so my question is that how, like, what exactly, like, how does it help exactly? Like, how is the ability of being in a superimposed states of the qubits actually lead to faster performances in large computational problems? Like, I'm not able to get my head around that.
Yeah, that's a good question. I mean, I think that's fair because I haven't really explained what's going on, for example, in this algorithm. Okay, so like, bear with me for a bit. So when I have a superposition over, say, a lot of states, what's I think more important than superposition is what I said was like interference is actually the more important thing that's going on. So if you like to think of the wave function as you have like 2 to the n branches of the wave function, and like if you like sci-fi, hard sci-fi, you can also think of it as 2 to the n different multiverses, or like different universes in like a large multiverse. And what interference is doing is, in some sense, you can sort of visit all these universes at the same time, and engineer these cancellations in the parts that in the parts where like a bad outcome happened, let's say. So you can reinforce computations that are going along in the direction that you want to, and you can cancel those computations that are not turning out so well. Again, that's like a very broad idea.
Yeah, thank you. I guess that helps. Like,
Okay.
yeah, it helps in understanding. Thank you.
Okay. Yeah. Sure. Yeah. So this was dequantized by Emin Tang, and what that means is she observed that the quantum algorithm has certain features, and she used that to give much faster classical algorithm. So like a popular blogger called Scott Aronson called this an application of quantum computing with 0 qubits. So you didn't need to actually build a quantum computer to see the speed up. You just used ideas from quantum computing and applied them in regular classical computer science. Yeah, so despite this dequantization, there are several problems for which large speedups exist. But again, there's also many other candidates where the speedup is only conjectured. So we have seen like heuristic evidence for like small system sizes. There's also like non-exponential speedups. And I think in the long run, I think it's safe to say that at the moment, we don't know what the best use case or application of quantum computing is going to be. So I think we have to keep searching for problems where we believe quantum computing can help. I'd like to actually talk about other implications of physics in physics, actually. And one thing I really like about this field is that even if quantum computers will never be built, quantum computing has already been useful in physics. And I was trained as a physicist, so I think that's where my sympathies lie. So one example is the black hole information paradox. So for a long time, it was thought by some people that black holes, just destroy information. Like you throw something into a black hole, and then the black hole evaporates after a long time because of Hawking radiation, and then now you ask, where did my information go? Um, and actually, Stephen Hawking himself believed that black holes completely destroy information. But that violates a lot of what we think is going on in quantum information, and that was deeply unsettling to a lot of people. So now we are getting some insights from understanding quantum complexity, which is a concept in quantum computer science. Yeah, it has also helped more generally quantum information, which is, I think, like a superset of quantum computing. Yeah, so like understanding concepts like entanglement has been really useful in simulations of quantum systems. And yeah, like my own research is of a similar flavor. What I enjoy doing the most is understand what the implications are, from tools of quantum computing and in other areas of physics. Yeah, so I'll just talk a bit about, yeah, is there a question?
Yeah, we have a couple of questions.
Sure.
Dinakar is asking, does making a quantum computer involve the usage of superconducting materials?
Yes, some hardware implementations do use superconductors.
Okay. Megang is asking, as we know that standard computer cells are fabricated and manufactured by silicon chip companies. Similarly, how are the singular cells or any physical hardware for quantum computers manufactured?
Yeah, again, I'll cover hardware soon.
Okay. And what about Deutsch algorithm? Does it have a practical implication?
So Deutsch's algorithm is no, but it's one of the very first algorithms to show that there is a difference between quantum and classical computing. But yeah, there's not a large speed up there. So I would say there's not a practical application there.
Okay. Thank you.
Okay, so there's a lot of companies these days who are invested in quantum computing. So let's see what they're up to. I'll just cover some hardware platforms and what are the advantages of each one and why people like it. So yeah, like, as someone asked, superconducting qubits are one of the leading candidates today. Like for example, Google's Sycamore chip is just based on superconducting qubits. And what you have essentially is an LC circuit. So you have something with an inductance and a capacitance, and yeah, that defines some energy levels, and you can manipulate those energy levels in a certain way. The advantages are that you can apply really fast gates and also read out the measurement really fast. Maybe one potential disadvantage is that the layout is two-dimensional. So each qubit can only talk to qubits that are nearby on this 2D grid. Okay, one more leading candidate today is that of ion traps. Essentially, there's there's a trap that traps ions. What it does is apply some electromagnetic fields and ensures that, say, ions, they're trapped in this nice chain like this. And one leading candidate is that of an alkali ion of ytterbium 171. The advantage here with ion traps is that they have really long coherence times, meaning that So there's some time with quantum computing. There's usually some time after which the results get spoiled, so as to say. And ion traps have really long coherence times, so that's a good thing. And actually, atomic clocks are based on ion traps. But the disadvantage with ion traps is that the operations are a bit slower. Yeah, but you can sort of make up for that with non-local gates. So you're not restricted to like 2D or anything like that here. There's also photonics-based schemes. So what you do here is store information in the state of a photon, and like free space photons, they're just moving along at the speed of light, and they don't usually interact so much with other things around them. So that's why they're a good carrier of information, because you won't lose the information. Yeah, but again, it's harder to make them interact. Another platform that I really like is that of Rydberg atoms. Yeah, what you can do here is, yeah, you store energy, you store information in 2 energy levels of a Rydberg atom. And in this figure, so you can actually use these beams of light to, you can use them as a tweezer to move around your atoms. And that was really cool. I think, yeah, so optical tweezers got, one, yeah, they were the reason why the Nobel Prize last year were awarded. And yeah, these Rydberg atoms have really strong long-range interactions, and they might also have possibly longer coherence times than, say, superconducting qubits. There's also many other platforms like solid-state qubits and nitrogen vacancy centers in diamond, nuclear magnetic resonance-based quantum computing. So this is actually really hard to scale up, but this was responsible for a lot of early work, like in the 90s and 2000s. So there's also quantum computers you can build based off of topological materials, and this is an area that Microsoft is pursuing. But like, yeah, I think this one hasn't been realized yet. And yeah, like I think the field is really wide open. There's a lot of options that we haven't even invented yet. So like a future quantum computer, say 30 years from now, may not look like any of the pictures I showed you. Yeah. So yeah, you may ask, when will I get one? When will Intel send me this quantum processing unit or whatever? Yeah, and yeah, sadly, I think the answer is not anytime soon. So I just want to alert you to the hype train. So there are really optimistic predictions of how much quantum computing is going to grow, and how, especially in the hardware side, like how many qubits we'll achieve by a particular year. So for example, this was a prediction in early 2018, which said that by 2020 we'll have like 1,000 qubits. Yeah, we didn't get there. And I think the reason is not just COVID-19, but just that our true progress is maybe not as optimistic as this line suggests. I estimate that I would probably need at least 10 more years to see like a nice, reliable, and useful use case in industry. Something that you can actually sell people to. Yeah, and so this person saying that current quantum devices aren't powerful enough to solve useful problems faster than classical computers. And yeah, like we really don't know whether they will be in 5 years or not. But meanwhile, while we we won't just wait for 10 years, right? There's a lot of potential for simulating physics. And interestingly, physics simulation is what accelerated the growth and adoption of early classical computers. Yeah, and so there's this catchphrase called NISC, which stands for Noisy Intermediate Scale Quantum Computers. And what can such quantum computers do? Again, this is like an area of active research at the moment. Yeah, so in the future, we'll continue to see investment in the field, both by government and industry and academia. And I'll just say briefly about Indian efforts, which has a new national mission for quantum computing. And yeah, I'm really excited about what possibilities this has. I should say that we really need a lot more talented researchers and practitioners from diverse fields to be at least quantum literate, if not expert in quantum computing. And so this is echoing this headline here. And what that means is just being aware of these broad concepts behind quantum computing, sensing, and communication. And yeah, like the more people we have working in this area, the faster we can discover new applications. Yeah, so here's a few resources in case you want to learn more. IBM has a quantum computer that's up on the cloud that you can just interact with and make it do things. So they have a nice tutorial here as well. And Michael Nielsen has a playlist of videos here. He also has longer videos and a really excellent textbook, which is how I learned quantum computing. And Scott Aronson regularly blogs about the latest news in quantum computing. So you can check out this blog here. And yeah, just while making these slides, I searched around and I found this really nice link that has some advice. Or maybe, yeah, so this has something for both at the undergraduate level and the high school level and so on. But yeah, maybe I'll just pause here in case you want to take a screenshot or something. Okay. Yeah, with that, I thank you. And yeah, if you're interested in learning more, feel free to contact me here or just, find me on this website. Thanks.
Thank you for that great presentation. I think the audience liked the meme a lot. I think we should, I'll just ask a few more questions that were put up, and we circulated a form as well before the talk. So there are some questions for that as well. Yashas is asking that how will decoherence affect quantum computer in the future?
Yes. So I alluded to decoherence earlier, but I think I didn't really make it explicit, using that term. So decoherence is when, for example, the environment measures the state of the quantum, the qubit before you do. So what that means is, yeah, like sometimes you don't have access to the information that you wanted. And decoherence is more generally just blamed for any error that we see. Yeah, so I really should have mentioned that. Like, yeah, decoherence is why we are not yet at the stage where we are building where we have millions of qubits and so on. Because even if you do build a million qubits, none of them are super reliable. And yeah, I think that's the big bane of the whole quantum computing field right now. So there are ways to overcome decoherence, and that's called quantum error correction. So error correction is again like a really interesting field, and interestingly, it also has implications in theoretical physics and again in black holes. But maybe that's not why you care about error correction. Yeah, error correction, theoretically gives you a way of fighting decoherence, and we are getting there. Yeah.
Are there any specific Indian research efforts that are being put into quantum computing as such?
So regarding experiments, I definitely know of a group in TIFR that pursues superconducting qubits, and other groups I'm not too aware. But we do have a lot of interesting work in theory going on at like the Harish Chandra Research Institute, HRI in Allahabad, the Institute for Mathematical Sciences in Chennai, um, and yeah, a lot of the IITs as well.
Okay. So one question was that how efficient is quantum computing in terms of energy consumption when compared to normal computing as such?
Ah, so that's a great question. I don't think people have paid much attention to that just yet, primarily because each hardware that you choose, the answer will be different. Um, yeah, I think it's really hard to say how the future how a future quantum computer is going to look like and how much energy it's going to consume. But in case you're interested in energy consumption, there is so Google did publish some results in their in their 2019 paper when they announced quantum computational supremacy. So they analyzed how much energy it costs to run the quantum computer, and how much it would have to run, say, a classical computer that was going to implement the same task.
Okay. Manushri is asking that a lot of programming languages like Qiskit and stuff do not have noise added to it. So would it be better working with NISQ sims or better using pure simulations?
That would depend on the answer. That would depend on what you're looking to gain from a simulation. So, yeah, like if I come up with, say, a NISQ, quantum algorithm. Sorry, where did I say? Never mind. Yeah, if I'm coming up with a NISQ quantum algorithm, and I'm really interested in whether the performance on like an actual device that's built by IBM, say, would be good or not, then it makes a lot of sense to use these NISQ simulators. But if I'm, say, benchmarking another application, like it's an application, let's say, for error corrected computation, then I perhaps don't need to consider all that.
Okay. Anirudh is asking that China's Zhuangzi is recently it took over Google's Sycamore. Does this mean that the quantum race is like a new space race?
So regarding the first sentence, I think this was very recent, like 2 or 3 weeks ago, and I think it's certainly interesting. I don't know if I would say that they took over Google. But like this, definitely similar elements as the space race being played out here. And again, what's interesting here is now that like it's much more permissive than space, in the sense that you don't just have nations competing, you have several companies competing, and so there's a lot of players in the space, so as to say. And I think that's interesting.
Okay. I think there's a widely popular question that as undergraduate students, how would you suggest we go about actually getting into the field or, just learning it? Yeah.
Okay, so let me like just go here and see what he says. Yeah, actually, so there are really nice lecture notes by John Preskill. Okay, so these are more physicsy. There's also lecture notes by David Berman, which are more computer sciencey. And so actually, I learned quantum computing as an undergrad, through this book itself. So I did some self-study, but I also then started working, in the field. Yeah, and I also used to read Scott Anson's blog during undergrad. So yeah, these are some ways to stay updated.
Uh, if possible, could you give us like a bit more insight as to how your journey went from as an undergrad physics student, integrated masters, to actually working in actively in the field of quantum computing?
Sure, yeah. Um, so I was fortunate to have had some contact with this institute called the Homi Bhabha Center for Science Education in Mumbai. It's actually a branch of TIFR. So they have this initiative for undergraduate science called the National Initiative for Undergraduate Science, NIUS. And what they had was, so they paired, first year undergrads with professors in physics. And, so because of this, I got to work with Professor SM Roy at TIFR on quantum information. And yeah, so I was mostly just always curious, and I tried to get my hands on whatever learning material I got. And yeah, I did a course in quantum information too, so that helped. Mm, yeah, like this was at IIT Kanpur. Uh, yeah, it was mostly coursework and reading a lot on my own.
Okay. So Yashas is asking that most of the attendees here are engineering students as such. So is there any advice that you would give them specifically, because it's we're not that exposed to physics as a whole?
Yeah. Actually, yeah, I think um, sometimes when you look at popular expositions of quantum computing, they tend to play up the quantum physics a lot. I think, okay, maybe I should add another recommendation here, which is a book by Scott Aronson called Quantum Computing Since Democritus. And I think that does a very good job of just abstracting away the physics of it. So what he just phrases quantum mechanics as like probability theory with minus signs. That's essentially all that's going on. Yeah. So it is possible to like pick up quantum computing without having too much physics background. In fact, a lot of like a lot of researchers, like even including Scott Aronson, they're computer scientists and not physicists.
Okay, that's actually pretty heartening to know.
Yeah.
Uh, does anyone have any other questions? We'll wait for a couple of minutes, so you guys can just raise your hand if you want and ask directly. GB Raghav Krishna is asking that is it possible to actually build a quantum computer at home? IBM gave some indication recently.
Oh, I'm not aware of that, but I think that's pretty hard to do. Yeah, but maybe I'm not being imaginative enough. Maybe you'll prove me wrong. That would be nice.
Yeah, I think having quantum computers at home would be really cool. Uh, okay. Uh, I don't think there are any other questions left.
Okay.
In that case, Suprati, could you just give the vote of thanks?
Shall I stop sharing?
Yeah.
Hello.
Yes,
Yeah.
yes.
All right. I'm so sorry for that. Okay. Now that the session has concluded, I'd like to thank our speaker, Abhinav Deshpande, and the moderator, Dhyan Gandhi, for such an amazing event. We'd like to also thank such an enthusiastic audience for asking such innovative questions for making this event successful. The talk has been very intuitive and has given us a lot of insight into the field of quantum computing. I think we all loved the memes that you put in between. It made the learning that much more fun. Most importantly, I think we've finally understood why quantum computing is so cool. All right. So I would also like to thank our entire team for making this event possible. We look forward to a continued response from all of you guys attending. We would also really like to have more of these interactions with you, Abhinav, if you would love to have us. Thank you so much, everyone, and have a good night.
Yeah. Thank you. Thank you to the team for making it all so smooth. Yeah. And to the audience for these really great questions. I really enjoyed this.
Uh, Thank you everyone for attending.
Thank you, everyone.
Yeah, I think we can leave.